Hello, hi everyone. So now we continue with the second subtopic for the curve fitting method, which is polynomial regression. Okay, now some engineering data is poorly represented by a straight line. So for this type of cases, a curve would be better to fit this data. One method is by using transformation, as been discussed previously. So another alternative is to fit polynomials to the data using polynomial regression, which is this subtopic. The least squares procedures can be readily extended to fit the data to a higher order polynomial. So for example, suppose that we fit a second order polynomial or quadratic with the equation of y equal to a naught plus a1x plus a2x squared plus e. For this case, the sum of the squares of the residuals is SR, as shown in the slide. Following the procedure of the previous section, we take the derivative of equation SR with respect to each of the unknown coefficient of the polynomial. As in the first equation, the SR equation is derived with respect to A naught. And then the second one is with respect to A1. And the third one is derived with respect to A2. These equations can be set equal to 0 and rearranged to develop the following set of normal equations. Note that the above three equations are linear and have three unknowns, which is A0, A1, and A2. The coefficients of the unknowns can be calculated directly from this observed data. The two-dimensional case can be easily extended to an mth order polynomial as the equation shown in the figure, which is y equal to a naught plus a1x plus a2x squared, and so on, and plus am x power of m plus e. For this case, the standard error is formulated as sy through x equal to set SR divided by n minus m plus 1. This quantity is divided by n minus m plus 1 because m plus 1 is a data derived coefficients used to compute the SR. Thus, we have lost m plus 1 degrees of freedom. In addition to the standard error, a coefficient of determination can also be computed for polynomial regression with the above equation. Okay, let's look at example 6 for the polynomial regression. Fit second order polynomial to the data in the first two columns of the table below. So by referring to the table, firstly, we need to calculate all the parameters needed for the equations. Thus, substitute all the value of the parameters into the equations and then simplify the equation to become a matrix. From there, solving all these equations and giving a naught equal to 2.47857, a1 equal to 2.35929, and a2 equal to 1.86071. Then, substitute the value of a naught, a1, and a2 into the least square quadratic equations as shown here. So it will become y equal to 2.47857 plus 2.35929x plus 1.86071x squared. The standard error of the estimate based on the regression polynomial is equal to SR, which is 3.74657. And the SY stroke X is equal to 1.12. From there, we can calculate the coefficient of determination, which is R squared equal to 0.99851. That indicates that 99.851% of the original uncertainty has been explained by the model. And the conclusion that quadratic equation represents an excellent fit as seen from the graph plotted. Before we go to the next subtopic, please do the exercise 3 on the polynomial regression. You can check your answer from the result provided in the lecture notes for topic 3. Alright, the third subtopic in topic 3 for curve fitting method is multiple linear regression. Okay, actually we are still in the linear regression, but this time we are dealing with multiple linear functions, which means 2 or more equations. So what is multiple linear regression? Is when the case where y is a linear function of 2 or more independent variables. For example, y might be a linear function of x1 and x2, as shown in the equation here. So y equal to a naught plus a1 x1 plus a2 x2 and plus e. Such an equation is particularly useful when fitting experimental data where the variable being studied is often a function of 2 other variables. So for this 2-dimensional case, the regression lines become a plane as in figure. Okay, figure here depicted of multiple linear regression where y is a linear function of x1 and x2. As with the previous cases, the best values of the coefficients are determined by setting up the the sum of the squares of the residuals, where the equation shows here. Then the equation for the sum of the squares of the residuals here is differentiate with respect to each of the unknown coefficients, which is a0, a1 and a2. The coefficients yielding the minimum sum of the squares of the residuals are obtained by setting the partial derivative equal to 0 and expressing the result in matrix form as shown here. So we can extend the 2-dimensional case to the mth dimension case as shown here, where y equal to a0 plus a1x plus a2x2 plus and so on until am xm plus e, where the standard error is formulated as sy through x equal to set sr divided by n minus m plus 1. And the coefficient of determination is also can be computed as previously, where r squared equal to st minus r divided by st. Although there are maybe certain cases where variable is linearly related to 2 or more other variables, multiple linear regression has additional utility in the derivation of power equations for the general form. So we can get here where y equal to a0 x1 power of a1, x2 power of a2, and so on until the mth order, which is xm power of am. Now, for the example of multiple linear regression, the following data shown here in the table were calculated from the equation of y equal to 5 plus 4x1 minus 3x2. Use multiple linear regression to fit this data. So for the solution, by referring the table above, calculate all the parameters needed for the normal equations here, and then transform to a matrix form. So from the matrix, we can solve for the parameters a0, a1, and a2, which is by using methods such as Gauss elimination, we can obtain the value for A0 equal to 5, A1 equal to 4, and A2 equal to -3. This result shows that it's consistent with the original equation from which this data were derived. Okay, do the exercise 4 by yourself for multiple linear regression to get better understanding in this subtopic. So the question is, use multiple linear regression to fit the data given below in the table and compute the coefficients, the standard error of the estimate and the correlation coefficient for this data. Check your answer with the results provided in the lecture notes. Now we go for the next subtopic, which is general linear least squares in the topic 3 for curve fitting method. Previously, we had discussed about 3 regression models, which is linear models, polynomial regression models, and multiple linear regression. In fact, these all 3 are actually belong to the general linear least square models, which can be expressed in these general terms of y equal to A0 Z0, A1 Z1 plus A2 Z2 plus so on until AM XM plus E, where Z0, Z1 until Zm are actually m plus 1 basis function. Now, let's see how the other 3 models of regression falls within this general linear least square model. Okay, for simple and multiple linear regression here, it falls within the model with Z0 equal to 1. Okay, substitute Z0 equal to 1, and then Z1 equal to X1, Z2 equal to X2, and so on until you get Zm equal to Xm. While for polynomial regression, it also can be included if the basis functions are simple monomials, as in Z0 equal to x power of 0, which is equal to 1, Z1 equal to x, Z2 equal to x squared, and so on until we get Zm equal to Xm. Note that the terminology linear here refers only to the model's dependence on its parameters, which is the a's. As in the case of polynomial regression, the functions themselves can be highly nonlinear. For example here, from the equations of y equal to A0 plus A1 cos omega t plus sine omega t, so we can see that the z's can be sinusoids, so it's nonlinear. Okay, let us look at the final subtopic in this chapter, which is nonlinear regression for the curve fitting method. The learning outcomes from this subtopic is, at the end of this lecture, you should be able to derive constants of nonlinear regression models and use the derived formula for the constants of the nonlinear regression models. There are many cases in engineering problem where nonlinear models must be fit to the data. In the present context, these models are defined as those that have nonlinear dependence on their parameters. For example, here, we have a function of fx equal to A0 multiplied by 1 minus e power of negative A1 x plus e. Note that the locations of the parameters a. This equation cannot be manipulated to conform the general linear least square models that had been discussed previously. As with linear least squares, nonlinear regression is based on determining the values of the parameters that minimize the sum of the squares of the residual. So for the nonlinear models, this solution must proceed in an iterative fashion. So one method, which is Gauss-Newton method, is one of the algorithm that can be used for minimizing the sum of the squares of the residuals between data and nonlinear equations. The key concept of the technique is, first, a Taylor series expansion is used to express the original nonlinear equation in approximate linear form. Then, least squares theory can be used to obtain new estimates of the parameters that move in the direction of minimizing the residual. Okay, for the first step, the relationship between the nonlinear equation and the data is expressed generally as y1 equal to function of xi, parameters a0, a1, and so on until am, plus ei. So where yi equal to a is the measured value of the dependent variable, the function of fxi with parameters of a0, a1, and so on until am is the function equations of the dependent variable xi. a0, a1, a2, and so on until am is the nonlinear functions of the parameters, and ei is the random error. So for convenience, this model can be expressed in abbreviated form by omitting the parameters. So it can be simplified to this equation. The nonlinear model can be expanded in a Taylor series around the parameter values and curtailed after the first derivative. Okay, after curtailed at the first derivative. For example, for a two-parameter case, we'll get function of xi j plus 1 equal to fxij plus derivation of f function of xij divided by with respect to a naught and multiply by delta a naught and so on, where j is the initial guess and j plus 1 is the prediction. So delta a naught can be obtained from a naught j plus 1 minus a naught j, and delta a1 can be obtained from a1 j plus 1 minus a1 j. Linearizing the original model with respect to the parameters equation 3.40 can be substituted into equation 3.39 to yield yi minus function of xij equal to derivation of fxij with respect to a naught multiplied by delta a naught plus derivation of fxij with respect to a1 multiplied by delta a1 plus ei. So this can be simplified into a matrix form of D equal to zj delta a plus e, where zj is the matrix of partial derivative of the function evaluated at the initial guess j. So this is the matrix for z. N is the number of data points, and derivation of fi to ek is the partial derivative of the function. The vector d contains the difference between the measurements and the function values, while the vector delta a contains the change in parameter values. The next steps, which is the second step, is to apply linear least square theory to equation 3.41, resulting in the following normal equation here. Thus, the approach consists of solving equation 3.42 for delta E matrix, which can be employed to compute improved values of the parameters as in this equation and this equation. This procedure is repeated until the solution converges, that is until the error equal to this falls below an acceptable stopping criterion. Now let us look the example 8 for nonlinear regressions using Gauss-Newton method. The question is, fit the function of a0 multiplied by 1 minus e power of negative a1x to the data given in the table. Use initial guesses of a0 equal to 1 and a1 equal to 1 for the parameters. Note that these guesses, the initial sum of the squares of the residuals is 0.0248. Okay, for the solution, the partial derivatives of the function with respect to the parameters are given here, equal to 1 minus e power of negative a1x, and with respect to a1 is equal to a0 e power of negative a1x. Both of the above equations can be used to evaluate the matrix here, the matrix of Z0. The Z0 matrix, when multiplied by its transpose, resulting in this matrix, which in turn can be inverted to yield this. The vector D consists of the differences between the measurements and the model predictions. The vector D then multiplied by Z0 transpose to give this matrix. The vector of delta A is then calculated by solving the equation of 3.42 for this, which can be added to the initial parameter guesses to yield the value for A0 and A1. So for the conclusion, the improved estimates are A0 equal to 0.7286 and A1 equal to 1.5019. The new parameters result in SR equal to 0.0242, epsilon naught and epsilon 1 equal to 37% and 33% respectively. This computation can be repeated until these values fell below the prescribed stopping criterion. The result is A0 equal to 0.79186 and A1 equal to 1.6751. This coefficient give SR equal to 0.000662. Okay, last but not least, do the exercise 4 to gain more understanding in nonlinear regression. The question is, use nonlinear regression to fit a parabola to the following data in the table. You can check your answer with the results given in the lecture notes. So that's the end of topic 3. Thank you for watching and listening to this video, and I wish you all the best.